To Dark Matter Materials. My name is Dr. David Antoniuk. I am the CEO of the company. My colleague here, Dr. Robin Hamilton, he is the inventor of the technology. He's the CTO of the company. And we have Dr. Stryker, who is also a founder of the company and co-inventor of the nanocatalytic technology. And somewhere around here is Dr. Vino. There he is. Dr. Vino, he is another co-founder of the company and also associate dean of the Faculty of Science. Okay, at the University of Alberta. All right.
Dave Scott.
And Dave Scott, the operations manager. All right, he'll be guiding you through getting your lab coats on and get your glasses and guiding up into the labs upstairs. Okay. And there's drywall dust, so just watch where you're walking. There's the construction going on up there. They're renovating. So we're going to talk a little bit about the company, and I'm going to go through a few slides, a little bit about who we are. So Dark Matter Materials is a spin-off from the University of Alberta. We this was through the discovery that Robin had in 2020, and 2021, yeah. And we had to look at the technology to actually understand what it was. And Robin and Jeff, we kind of know each other from the university, and so they approached Applied Quantum Materials, which is the parent company, and because we know how to make silicon nanomaterials. And so what we did was we looked at this and we started doing business analysis, et cetera, and looked at the technology because nobody could understand what Robin did. Anyway, so what happened was that we had to get the data and everything else, and as a result of that, we formed a new company in July of 2022. And here's examples of a couple of the nanopowders and stuff like that. But the team has actually been doing research in catalysts for, I think it's over 35 years or something like that.
Oh, well, and Robin and I have been partners for 15, so yeah, it works.
So I want to talk a little bit about the hydrogen economy. As you know, hydrogen cannot be, it doesn't occur naturally. It must be synthesized. Now, the primary areas to get hydrogen is from cracking methane, essentially. You can do it through various techniques, but and they have these colors and things like that, whether or not they're blue or gray or turquoise, depending on how they do that. Now, we have the alternative is electrolysis, what we were talking about just earlier. Now, unfortunately, it only accounts for a minuscule amount of the overall global production of hydrogen, and it consumes electricity, and you need to split distilled water. In other words, you need to heat the water up in the first place, distill it, and then you can do your electrolysis. So what they don't tell you on the costs of electrolysis is the initial heating and preparation of the distilled water. So in the particular marketplace, hydrogen, green hydrogen, it competes with its own energy source. You've got to create green electricity, and then you got to convert it to hydrogen, and then you run a fuel cell and make electricity. So it's not really our view, not a really viable option. So water gasification, without sunlight or electricity, have been considered an unsolvable problem for hundreds of years. So in looking at the hydrogen economy, there's the hydrogen production, which people can do fairly cheaply with autothermal reforming and methane pyrolysis, etc. But to get it to the end user, what you need is all this stuff in the middle. You need the packaging, the distribution, storage, all of that stuff costs more money than it costs to get the hydrogen in the first place. So, in other words, to the end user, the price is high. But what we do, we get rid of that middle part because we make hydrogen on demand. So what are we talking about here? It's next generation catalysts. We are producing environmentally friendly, highly active catalysts that we can use for hydrogen production, ammonia production, plastic recycling, and batteries. This catalyst family can do all of these things. And there's even more that we've also been playing with that we've discovered about CO2. But we won't talk about that. So we're going to talk about two things today, the hydrogen production and the battery technology. So on the hydrogen production, we have a patent pending technologies. There's actually, we filed one, there's several more that are in the progress of being filed. So this is, the technology is that we can produce hydrogen from any type of water under mild conditions. So from room temperature to, elevated temperatures.
Any type of water, like wastewater?
Wastewater, yes.
Work with tailings water.
Yes.
We've used tailing pond water, we've used tea,
Can you do stuff with organic compounds in it?
yes.
Yes, bitumen tailings ponds are high carbon.
So gray water from your home.
Thinking paint sludge.
So any of these type of waters can be used, and we've tried just about everything, I think. So the catalysts are also inexpensive. We get the materials they're environmentally friendly, they're common, abundant materials that we make these nanocatalysts out of. And this process will work at actually room temperature, which is unheard of, and nobody believes us about that until they see it.
By room temperature, you mean it can be done in room temperature? Like I thought there was a heat involved
Yes.
as well as.
You can, well, I'll show you a video next, which actually shows it working at room temperature. We just pop the thing in, little pellet or whatever in the water, and it'll start bubbling. We can do it at room temperature. Now, the other thing is that if you elevate the temperature, you get a little more reactivity and things.
You add heat to go faster.
It just goes faster.
So I assume you could use waste heat from a different process.
Precisely.
Exactly.
That's our intention.
Oh boy, I got a question for afterwards.
So the waste heat just makes it more effective.
Yes, that's right.
So it can work at room temperature, or works better if it's at elevated.
Yep.
Yep.
There'll be a slide where
We'll
it's
explain.
it's shown pictorially.
Okay, I'll ask the question now. Waste heat, you can use waste heat, right?
Yeah.
And I don't know enough about this, but if hydrogen fuel cell does it create heat? So could
No.
it can't be a virtuous circle.
No.
It can't be a virtuous. Okay, done. Stopping.
So we don't use any precious metals either. So that's another, the whole point of this thing was if we could make these nanocatalysts cheap and simple and reusable, then we could have mass markets for it. So, this is the results of what our production is. You may have seen some work out of University of Santa Clara, MIT just recently. We're doing a whole bunch of stuff. They're using aluminum, gallium, indium. We're not, and look at the results. We're 40 times more hydrogen production from them. And that's just room temperature. We put a little wafer in and it's generating hydrogen bubbles right there. Now to speed it up, what you'll see upstairs is we've speeded it up. For an engine we needed a little more oomph, as it were, and what we're able to do is, so we heat up the water a little bit and we accelerate the reaction, and literally it just goes, you'll see it. So example, so that wafer is just a common material that we use, and we just pop it in the water and you'll see it just bubble and produce all this gas. All right, so hydrogen from thermal chemical water splitting, that's what we do. So what we have is we have water, we have a support mechanism, and the catalyst. And we have room temperature to 100 degrees. We put it in our reactor. No precious strategic metals used, no greenhouse gases or carbon capture requirements at all. So we produce hydrogen. So hydrogen for transportation, refueling stations, industrial, residential, on-off grid, heat and power, chemical production. And these are the companies we're talking to right now on these areas. So we actually have non-disclosures and and scope of works being developed to actually work and integrate our technology with these companies. Now, that's on the hydrogen side. On the sort of the waste side, what we have is a support mechanism, the catalyst and oxygen, and what that gives us is battery electrode materials, polymer recycling, and ammonia production. And we're working with the following companies to do this technology. We've got quite a lot of interest from all of these companies, and they sought us out, not the other way around.
Is it doing both at one time, or is that two different processes you're describing right now?
So, go ahead, Rob.
Good
Two
question.
different processes. So the oxygen has to go somewhere. Everybody asks, where's the oxygen go? We keep it there, because then we could use it for other reactivity. This kind of goes back to our recipe analogy. Well, you put a little bit of oxygen in there, and all of a sudden we can do other chemistry.
And so you're combining with other materials to turn it into battery?
No, the oxygen will combine with the catalyst materials, make a new catalyst that we then use for this.
It's amazing, really.
Fuck.
So,
You know, I use that too.
so to show you how this catalyst works, what we have is the support, we have the water, and we have the catalyst, and we create this activated complex. And what it does is it reduces that energy barrier to go from one state to the other state to produce the hydrogen. Instead of that big hill to climb up normally that you would have, the catalyst reduces everything to room temperature. There's enough energy in that amount that will make this thing work. And we produce 99% pure hydrogen out of this process.
May I ask, you're using all this other material, bitumen, gray water. Where do, without separating them into distilled water, where do the other chemicals and how do they react? Do they not simply react whatsoever with the catalyst? Is that what's happening?
There would probably be some reaction, because it loves to chew up organics. As soon as you make that kind of thing, just
Yeah.
like, because organics, plastics are all
Yeah,
organics,
yeah.
it would start to chew those up,
Yeah,
and start making them smaller and smaller and smaller and smaller.
okay.
The benefit perhaps for tailings water is that there's a lot of strategic metals in tailings water. So people are actually looking at getting lithium out of tailings water. Well, if you run this reaction and you go to completion where it consumes all the water, all you're left with is the value added materials in the bottom. So there may be some economic pathway to using tailings, making the hydrogen out of the tailings water, and then getting the strategic metals out of it.
So the hydrogen bubbles off, so
Yes.
it self-separates.
Yes.
And then what's left over is these constituent materials you're talking about?
Yes.
Okay.
Yeah.
Okay.
And we don't have to recycle. We
Okay,
use
okay,
another.
okay.
You use a lot less electricity, but where is the electricity consumed in this?
The heating process.
That's
Just
So
heating
you-
up to the water,
But
heating
you
the water.
can
to
also
the-
run it without heat.
Yes.
So just if you want
Yeah,
to,
you mean there's gonna be some mixing, so there's always gonna be some,
but it's not a lot.
What's the
Yeah.
difference in the rate with heat?
oh, it's quite a bit,
Yeah.
yeah.
Like, is it 2 times, 5 times, 10 times?
So chemists will give you, I have to go chemist nerd for a second, about every 10 degrees is about doubling the rate. So going from room temperature up to 100, so you know, go from 20 up to 30, it's double. From 20 to 40, it's 4 times, and so you can keep on doing those
So it's like,
iterations.
it's like 16 times or something?
Yeah, something like that.
Okay.
Yeah.
That's a rough guess.
Okay, thank you.
So what we've done is we made a highly active catalyst. So the synthesis method as we've developed is we make nanometer sized particles, and we make it in large quantities where the scalability is not a problem. We made it in Canadian Tire buckets, you know, literally stirring at room temperature, we make this catalyst. It's that easy to make, but it's complex in the chemistry to how to make it all work. Now, as we talked about, there's a wide range of applications, including, you know, reducing agents and battery materials, etc., from this catalyst family. We replace precious metals. So we can replace metals like a lot of catalysts use platinum. We can change that. We believe we can change catalytic converters using this catalyst as well and get rid of platinum.
Well, get sold somewhere else. There isn't enough platinum on Earth for the demand. This would free up, I
So-
don't remember the statistics, but.
We actually can take the waste product, as it were, and we can use those for semi-solid state electrolyte battery anodes and cathodes. And we'll talk a little bit about the batteries and stuff in a second, but we can actually use that other product to make batteries. So nothing goes to waste. So now what we have is, we've got nanoparticles replace precious metals. They're low cost, low energy to actually make them. They're highly reactive at low temperatures and pressures, increased catalytic activity over anything we've ever seen before. We can regenerate the catalyst many, many times, so we can just recycle these catalysts, etc. And they're extremely environmentally friendly. There's no toxic metals at all with this technology. So our value proposition. We offer a decentralized approach to producing hydrogen. Make it anywhere. It doesn't involve new infrastructure, no transportation, networks, building pipelines, not really required for our technology. We can do it anywhere. The hydrogen, we can make hydrogen fueling stations anywhere. You have a source of water. If we have waste heat, as Robin was saying, you don't even need the reactant material. You can just use the catalyst itself. So we were talking to some cogen folks and stuff like that about using all their waste heat and things like that coming off their systems, and we just make hydrogen out of it and
We have
make it really simple.
cogen site at our manufacturing site in Ontario, and that's why I'm asking.
Yes, exactly. So the hydrogen can be fed directly into a fuel cell, and I'll show you a
It's
video
not
on
clean
that.
enough though, right?
It is clean enough.
At
It-
99%?
It's 99%. I'll show you a video of it's how it works. We don't need potable water again, and water now becomes your energy carrier. You carry around water. The whole process is very highly energy efficient. We're not wasting anything by going from electrolysis to fuel cells to hydrogen, and all that stuff like that. We don't waste anything. And lastly, there's no GHG emissions whatsoever. So, looking at hydrogen adoption challenges and solutions. In terms of electrolysis, it takes 50 kilowatts to make 1 kilowatt hours to make 1 kilogram of hydrogen. With our solution, we're doing it between 2 and 8 with the same with our process. The number varies because of temperature conditions and water conditions and things like that. But this is our range that we've seen, and we're always trying to improve. In terms of fresh water, you need for electrolysis, you need 100 liters of distilled water for 1 kilogram of hydrogen.
How are you getting it from 100 to 20 if you're starting with water?
So,
Okay, so the 100 liters, that is vastly more than you actually need to make 1 kilogram of hydrogen. If you just look at the stoichiometry about how much water you need for that. So it's more that they have to have theirs kind of dilute in a bath, but we can run ours concentrated. So it's the strength of your team, in a sense. You don't need that much water for electrolysis, technically, but for it to work well, you do. And for us, we can just run a much more concentrated reaction.
If I can ask perhaps a more difficult question. The 50 kilowatt hours to 1 kg versus the 2 to 8. Other than the platinum and precious metals needed for electrolysis, the 50 kilowatt hours is the real killer for electrolysis.
Yes.
I don't know what your price is here, but in Quebec, even with cheap electricity, it's what, 8 cents a kilowatt hour?
It's about 8 cents.
Yeah, it's
8 cents.
8.88 here.
Yeah, 8.8. So that you're looking at $4 just with electricity.
Yeah.
No wonder hydrogen is expensive.
Yeah.
Okay, so you got $2, 2 kilowatt hours, let's take the best case scenario, you got 1/5, you got 60, what was $4 is now 19 cents. I read somewhere in your site, it says 6.50.
Yeah, that's the price of like the materials that we would add, like, so the electricity would cost like 15 cents. And then that is more when we're looking at how much catalyst and material we can make at one given time, and as you scale up, the price comes down because you can buy in bulk.
I understand, but
And that's the one-time price, because we recycle, regenerate that catalyst over and over again. So every time you use that catalyst, the price drops.
David, you got
Never
5
gets-
minutes.
never gets consumed.
okay.
You got
So-
5 minutes.
It does not get consumed.
Because 650 a kilogram isn't gonna save the planet.
No.
I mean, it ain't gonna do it. People are already saying they can get there with electrolysis.
For industrial, we need about $1.
And for cars, you need 2, roughly,
Yep.
$1.50, $2. Can you get there? Yes or no?
We think so, yes.
Okay.
So,
Same, if you use,
Give them only 2.
if you use wastewater, the other material in the wastewater that you don't want,
you filter it out.
does it just come out as a sludge or?
Yeah.
Yeah, it would be a sludge, or you do a pre-filtration to get a lot of the sludge out, and then you throw in some stuff that has some sludge, but not the full sludge.
So in our solution, we've actually done much less than 20 liters to get 1 kilogram, but we're saying 20 right now because but we've dropped that by half already, essentially. Now, the problem with hydrogen, the fueling infrastructure is high cost. You need giant facilities. What we do is we can make hydrogen anywhere, so we cut that cost right down and eliminate all of that middle infrastructure. So now we have a generator. You can use it as a fuel cell, a chemical production, or hydrogen engines. We can use it for any of these applications. The impact to Alberta could be huge. Decarbonize the oil and gas industry, reduction of greenhouse gases, accelerating a practical, low-cost hydrogen economy. And the jobs, the investment, and things like that could be enormous for what we're trying to do here. And we've already established a number of indigenous partnerships with groups, because up north they run everything on diesel, and they can't get solar and wind that don't work for them up north. So, but they got lots of water, so hydrogen works really good for them. So we've got these partnerships going with these folks.
Are you seeing, you mentioned hydrogen engines and everything else, and this can be done in situ, you don't need tanks. Have you even thought, can't imagine the size of this, are you thinking of having onboard for cars and or trucks, where you have an onboard reforming or whatever, and it's just a continuous flow, and you just show up someplace and add wafers and water? Is that basically what you're after?
Yeah, we have some preliminary designs of reactors that are cartridge systems.
Okay, would they be small enough for cars or only for big trucks?
Easier to do with big trucks, obviously.
Okay, so big trucks are doable, for sure. Okay.
There's lots of room. Cars, well, it'll take some work, but we're getting there. So I'm gonna show you a little water to electricity demo. So this is, we have, in the back there, we have, I think there's 140 milligrams, less than a gram of catalyst. And it's just at room temperature, it's producing hydrogen. From that little reactor there, it's producing hydrogen. It's going through the little bubbler, you see the little bubbles, you know there's gas coming through, and we're feeding it directly into a fuel cell that's producing electricity. If you notice, there's no oxygen connection, it's just sucking it from the air. It's just pulling oxygen from the air and making that fan go. And that's just a small amount of our catalyst and how it works. So, I'm gonna go on to do a couple of slides on batteries, and
Be pretty
David,
quick,
Dino,
though.
we got a demo. It's
Got a
ready to
demo?
go, it's running, so please.
all right, so the batteries, we make from this material, we make batteries out of it. And our batteries are really simple. We have a separator, 2 electrodes, which are the same, and graphite charge collectors. So the electrolyte is water-based, non-toxic, non-flammable, and the electrodes are the same material, so they're rechargeable. and we can mold them, we can make them in any shape we want. So, it's a couple of things what they look like. So there's a 12-volt battery setup. We actually made our logo with this stuff. So for future development, we're increasing the performance of these batteries. We're looking at the possibility of moldable batteries to fit them into odd shapes. And right now, we're achieving 3.4 volts plus. We've actually done 4 at once, but we're already. And this is just a very simple, non-toxic, safe battery system that we've been able to make. So applications, lots of applications, you all know about this and stuff like that. So no, again, no precious metals, no strategic metals, 3.4 volts and climbing. And this is our new semi-solid state battery technology that we're also developing, and it's using the same materials as the hydrogen production. And that's it. Now it's time to go.